Hello, in this video we're going to be talking about recursive functions or sequences. So by definition, recursive functions or sequences is the sequence that in order to find the current value I must use the previous one, either one previous one or two or three, whatever previous ones we need to find. Let's see examples. So if S1 is equal to 2 and Sn is equal to 2 times S of n minus 1. That means if I need S2, I must use 2S of 2 minus 1, meaning the previous one, which is S1. So 2 times S1, S1 is given as 2. That means I will get 4. S3, for example, will be 2 times S3 minus 1. Or we could say 2 times S2. So I need the previous one, which is 4. 2 times 4. S4 is 2, basically S3. Because I'm using the previous one, which is 2 times 8 is 16. And so on. Let's see this example here. So T1 is defined as 1 and Tn is use the previous one, which is Tn minus 1, add 3 to it. So if I need T2, I'm going to say it's T of 1 plus 3. And 1, T of 1 is 1 plus 3 is 4. So T3 become, use the previous, which is T2 plus 3. That means 4 plus 3. That means 7. T4 and so on. It's T3 plus 3 plus 3, which is 10. So as you see, I'm always using the one before, and I used 1 here, and add 3 to it. Let's see another example. Here it says find the first 5 values of the sequence. So A1 is given as 2, and AN is equal to 1 over the previous one, A of n minus 1, for all n greater or equal to 2. So A2, meaning 1 over A1, the previous one, which is 1 over 2. A3 is 1 over 1/2, which is 2. A4 is 1 over 2. A5 is 1 over 1/2, which is 2. So basically the sequence is given as 2, 1/2, 2, 1/2, and 2. These are the first 5 values of this sequence defined as follow. Let's see one more example here. So A1 is given as 1, but AN is given as n squared P of n minus 1 plus n minus 1. So here we have to see P of n minus 1. That means here we use the previous one, but the rest we use n squared or n minus 1. So P1 is given, P2 will be n squared, which is 2 squared, P of n minus 1, which is 2 minus 1, 1, plus 2 minus 1, 1. So right here, 2 squared is 4, and P of 1, we use 1, plus 1, which is 5. Now P3, 3 squared, 3 minus 1 is 2, plus 2. Because plus n minus 1, which is 3 minus 1, which is 2. 3 squared is 9. Piece of 2, that's what I used now, this one here. And now I'm going to use this one here. 5 plus 2, which is 45 plus 2 is 47. Now P4, which is 4 squared, P, 4 minus 1, 3, plus 4 minus 1, 3. So it's 16, and again P3 we just found it to be 47 plus 3, and this gonna give me 755. P5, again 5 squared, P 5 minus 1 is 4, plus n minus 1 or 5 minus 1, 4. So again 25, use the previous one, plus 4, which is a big number, 18,879. So the first 5 in the sequence is 1, 5, 47, 755, and 18,879. As you see, some of the sequences grow faster, this recursively. So, one famous recursive sequence is the Fibonacci sequence, based on the name of the Italian mathematician Fibonacci. So here what he has is he's defining f1 and f2. So the first and in the sequence is 1, the second is 1. But he's saying, for example, if you need f3, add fn minus 1, which is basically f3 minus 1 is 2, plus f3 minus 2 is 1. That means if you need f3, add the last two, which is 1 plus 1, which is 2. Now if I need f4, which is basically 4 minus 1, it's 3, plus 4 minus 2 is 2. As you see, if I need f4, I need to add the previous 2, which is 2 and a 1. So 2 plus 1 is 3, and so on. This is how it's defined. So the f5 will be f4 plus f3, which is f4 is 3 and f3 is 2, which is 5. So let me write this 1 1, and if I add this last two, so it is quicker how you do it. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 2 is 8, 8 plus 5 is 13, 13 plus 8 is 21, and so on. So you just add, if you need the current one, you add the previous two in the sequence. So this is by definition, every time you see big F in this textbook, meaning it's a Fibonacci. And let's see, here it says prove the given property of the Fibonacci number directly from the definition. So just by using the definition, go from left hand side and you'll find the right hand side. So if I start with the left hand side, using the definition, it's fn minus 1 plus fn minus 2. Again, if I use the definition again, fn minus 1 will be fn minus 2 plus fn minus 3. So fn minus 2 can be split into fn minus 3 and fn minus 4. So when I stop and think, what do I need to get into the right hand side, which is 3 of fn minus 3 and 2 of fn minus 4. So I'm not there yet. So what we do, I'm gonna again take this fn minus 2 and split it into fn minus 3 plus fn minus 4. And I'm writing down the other two. So let's see now, how many fn minus 3 do I have? 1, 2, 3. So I have 3 fn minus 3. How many fn minus 4? I have 2. And this is the other side, the right hand side. And we're done. So we started from the left hand side to the right hand side. So when it says the question, given the properties, use the definition of Fibonacci, you just have to split it or combine it until you get from one side to the other. The next example here, it's not using the definition. Every time you see dot, 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 to prove this Fibonacci number, we need to use proof by induction. So we're going to check for the smallest. What is f of 1? Is f of 1 really f of 1 plus 2, which is 3, minus 1? Where is f of 3 in Fibonacci? So you start with 1, 1. The third one will be at the last two. It's 2. So f of 3 is 2. So is 2 minus 1 equal to 1? Since f of 1 is 1, 1 equal to 1. So we have here 1 equal to 1. That means we check the first base number n equal to 1. The next thing I'm going to assume that f of 1 plus f of 2 plus all the way to f of n is equal to fn plus 2 minus 1 for all n greater or equal to 1. And we need to prove n plus 1. What does it mean? I need to prove that if I move all the way, instead of stopping at n, we go to the n plus 1. So where is it? It should be equal to, replace n with n plus 1. So n plus 1 plus 2 is n plus 3 minus 1. So this is where we need to check. So just like the previous, just like we did before, from the assumption we have f1 plus f2 plus all the way to fn is given to us as fn plus 2 minus 1 plus fn plus 1. We need to get to the right hand side, which is f of n plus 3 minus 1. So now let me rearrange this. Where would f of n plus 2 plus f of n plus 1 be? You know, this is also Fibonacci. So the previous ones, if one was f of n plus 2 and the other one f of n plus 1, that means it's gonna be equal to f of n plus 3. You could do the number line and just picture it. So if this is f of n plus 3, this one is f of n plus 2, and this one is f of n plus 1. So these are the previous ones. So if I add the previous one, I get the next one, and this is by definition of Fibonacci sequence. So right here, this is the same as f of n plus 3 minus 1, and we're done. This is true for all n greater or equal to 1. So we proved the n plus 1, and therefore we're done with the proof. Thus, if I add all Fibonacci sequence, it's the same as f of n plus 2 minus 1 for all n greater or equal to 1.